astronauts. In this video, we'll explore how lift producing wingtip vortices can lead to induced drag, affecting an aircraft's performance in flight. Additionally, we'll examine ground effect, explaining why planes seem to float just above the ground during takeoff and landing, and how it influences lift and drag. Finally, we'll tackle the topics of stalls and spins, discussing their causes and how pilots can avoid or recover from these potentially dangerous situations. So whether you're an aviation enthusiast, a student studying aerodynamics, or simply curious about how airplanes defy gravity, this video is for you. Now let's get started. Let's delve into wingtip vortices and induced drag. It's essential as they have a significant impact on flight. Gaining insight into these phenomena is crucial for enhancing aircraft performance and ensuring safety in flight. Wingtip vortices are a result of lift creation during flight. As an aircraft generates lift, the high-pressure air beneath the wings seeks to equalize with the lower-pressure air above, resulting in a swirling motion known as wingtip vortices. This swirling motion is a consequence of the conservation of angular momentum, giving rise to characteristic spiraling vortices. These vortices persist in the aircraft's wake, called wake turbulence, which poses a significant consideration for pilots. Pilots must maintain a safe distance from the aircraft ahead to avoid encountering the turbulence generated by these vortices. The strength of wake turbulence varies based on factors such as aircraft weight and configuration. Heavy aircraft tend to produce stronger vortices, leading to more potent wake turbulence. Typically, the wake turbulence is most pronounced during takeoff and landing when the aircraft is operating at lower speeds and higher angles of attack. Pilots must remain vigilant and adhere to prescribed separation distances to ensure safe operations. While wingtip vortices demonstrate lift creation, they also produce induced drag. The downwash caused by these vortices impart a rearward and slightly upward component to the airflow, leading to induced drag. Engineers designing the wings employ various strategies to minimize induced drag and optimize aircraft performance. Implementing winglets or modifying wingtips is one such strategy which helps reduce the strength of wingtip vortices, thereby mitigating induced drag and enhancing fuel efficiency. Ground effect, a fascinating phenomenon in aviation, occurs when an aircraft flies in close proximity to the Earth's surface, typically within half a wingspan or so. During this proximity, the aerodynamics of the aircraft undergo intriguing changes. One of the primary effects of ground effect is the enhancement of lift and reduction of drag. As the aircraft approaches the ground, the air that is normally spilled around the wingtips, that is the wingtip vortices, is trapped, creating a cushion of air beneath the wings. This cushion reduces induced drag and increases lift, making the aircraft more efficient in terms of lift-to-drag ratio. Ground effect plays a crucial role during takeoff, providing significant advantages. As an aircraft accelerates during takeoff, it enters ground effect, experiencing a sudden increase in lift. This allows the aircraft to become airborne with a shorter takeoff distance, contributing to more efficient takeoffs. Similarly, ground effect influences landings by providing benefits such as increased lift, enabling a smoother and shallower descent. This results in reduced landing distances and softer touchdowns, enhancing both safety and control. Equally, pilots must also be mindful when aircraft approach at higher speeds during landing. They may experience a prolonged floating. This occurs because the increased airspeed intensifies the cushion of air beneath the wings, enhancing lift and delaying the aircraft's descent onto the runway. As a result, pilots may find it challenging to initiate a timely touchdown, potentially leading to longer floating distances before the aircraft settles onto the runway. This extended floating phase can affect landing precision and require careful control inputs from the pilot to ensure a smooth and timely touchdown within the desired touchdown zone. You can see how this can be a potential problem in airports with shorter runways. Ground effect also presents other challenges. Pilots need to be aware that ground effect diminishes as the aircraft climbs, potentially causing a sudden loss of lift. This requires precise control inputs to ensure a smooth transition from ground effect to normal flight. Soft field takeoffs exploit ground effect to optimize aircraft performance on challenging surfaces like grass or unpaved runways. Skilled pilots deliberately utilize ground effect during the initial stages of a soft field takeoff, allowing the aircraft to ride on a cushion of air just above the surface. This technique reduces the power required for takeoff, preventing potential bogging down in soft terrain, and exemplifies the strategic use of aerodynamic principles in navigating challenging operating conditions. So, what is a stall? Well, it's a lot like engines coming to a complete stop. In aviation, a stall happens when the wing isn't producing enough lift to keep the aircraft in the sky. There are a couple of things that can lead to a stall. One big factor is exceeding the critical angle of attack. That's an angle of attack above which the air can't flow smoothly over the wing. Exceeding this critical angle causes the airflow over the wing to become turbulent and separate from the surface. This disruption in airflow reduces lift production, causing the stall. The critical angle or stalling angle of attack is typically around 15 degrees to 18 degrees for many airfoils. So how do you know if a stall is happening? Well, the aircraft might start to shake. You could hear a stall warning, accompanied by a buffeting sensation or a nose-down pitch of the aircraft. Additionally, the controls may become less responsive, and the aircraft may exhibit a tendency to roll or yaw unpredictably. The good news is, pilots are trained to deal with stalls. To recover from this stalled condition, the nose is lowered, the angle of attack is reduced, and power is added. This helps the air flow smoothly over the wings again, and the wing produces lift with the aircraft flying smoothly again. Avoiding stalls, particularly at low altitude, such as during climb-out after takeoff and during approach to landing, is paramount in pilot training. Pilots meticulously monitor airspeed, angle of attack, and other critical factors to ensure the aircraft remains in its optimal flying state. What exactly is a spin? In aviation, a spin is a specific type of stall where one wing is more stalled than the other, causing the aircraft to enter a rotating descent. Spins usually happen when an aircraft is in an uncoordinated state, meaning it is not flying straight. This can occur if one wing is at a higher angle of attack than the other during a stall. Spotting a spin is quite distinctive. The aircraft starts spiraling and the nose points downward. During a spin, auto-rotation occurs due to an uneven distribution of lift across the wings. This imbalance in lift, often caused by factors such as asymmetrical stall conditions or control inputs, results in a rotating motion around the vertical axis of the aircraft. Essentially, one wing becomes more stalled than the other, leading to a difference in lift generation. The wing with slightly more lift creates a rotational force towards the other side, initiating the spinning motion as the aircraft descends. This auto-rotation phenomenon is a critical aspect of understanding and recovering from spins in flight training and aviation safety practices. Spins are not something you want to experience unintentionally. Fortunately, pilots undergo thorough training to recover from spins. The essential steps involve decreasing the angle of attack to exit the stalled wing condition, applying opposite rudder to halt the rotation, and returning the nose to a standard flying attitude. Of course, the best strategy is to avoid spins altogether. Pilots do this by maintaining coordinated flight, managing the aircraft speed, and avoiding extreme angles of attack. We have delved into several crucial aspects of aviation: wingtip vortices, induced drag, ground effect, stalls, and spins. Grasping these concepts is vital for any aviator. If you found this journey through the skies intriguing, hit that like button. Feel free to share your thoughts or propose topics in the comments below, and don't forget to share this video with your friends. Until next time, fly high and stay curious.